Let us take a bird's eye view on classical and quantum computation. So here we start with what's a task. Right? So in classical case, so the task is a Boolean function. So it's a function that operates on n-bit strings with values with m-bit strings. Right? So this is a Boolean function. So for quantum computation, so the task is an element of a unitary group. And this unitary group is U of dimension 2 to the power n. Right? So this is the case when we have an algorithm, a task that involves n qubits. So then we distinguish between the task and the algorithm. So what's an algorithm? In classical case, algorithm is a decomposition of this Boolean function f as a composition of elementary Boolean functions operating on one or two bits. And so these elementary functions are AND, OR, and NOT. Now, so what's an algorithm in the quantum case? Right? So if we call this element T, so then a quantum algorithm is a decomposition of T into a composition of elementary quantum gates each operating on a small number of qubits, on 1, 2, or 3 qubits. And so here we include 3 qubits because the quantum analogs of AND and OR, so this will be permutation gates that operate on 3 qubits. So because in quantum case, so we need to take together input bits and output bit, right? So this classical AND has 2 input bits and 1 output bit. So its quantum analog operates on the space of 3 qubits. With this point of view, the complexity of an algorithm is the number of constituents in this decomposition. So either the number of elementary logical gates that are used in decomposition of a Boolean function, or the number of quantum gates, elementary quantum gates, required to implement a given quantum task. And so usually in the theory of computation, one looks at these complexity issues asymptotically. So this means that we are not going to fix the number of bits, right? And so consider our task as a parametric task depending on n. So for example, if we are talking about factoring a large integer, so this could be the n bits, the size of the integer that we need to factor. And when we look at complexity, we usually study complexity asymptotically. So what's the asymptotical behavior of complexity as the function of number of bits? Next, let us discuss the elementary quantum gates that we need to be able to realize various quantum algorithms. Let us start with 1-qubit gates. So these are unitary transformations that operate on the space of 1 qubits. So recall that the space of 1 qubits is two-dimensional. So this means that we are talking about the group U2. So 2 by 2 unitary matrices. Now let's start with the things that we already know. So we have a NOT gate. Right? So the NOT gate is the following transformation. It transforms 0 into 1 and 1 into 0. So the 2 by 2 matrix that corresponds to this transformation is the following. It's 0, 1, 1, 0. Right? So it switches two basis vectors. So then we also had the Adamar transformation. So this is the transformation H, which sends 0 to 1 over square root of 2 times 0 plus 1 over square root of 2 times 1. And 1 is being sent to 1 over square root of 2 or minus 1 over square root of 2, 0 plus 1 over square root of 2, 1. And so the matrix of H is 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, and 1 over square root of 2. Now, what are other gates that we can create? And so recall that this transformation should be unitary. Well, we can consider rotation gates. So here we can take rotation matrix R alpha. So this is the following: cos alpha, sine alpha, minus sine alpha, and cos alpha. Right? So here, the 0 first basis vector is transformed into cos alpha times 0 plus sine alpha times 1, and 1 is being transformed into minus sine alpha times 0 plus cos alpha times 1. So in particular, we see the Adamar gate is a special case of a rotation gate. So the Adamar is equal to rotation with angle pi by 4. Now, in addition to rotations, so we also want to use the following gate. So we'll consider the gate S alpha, which is the following, has the following matrix: 1, 0, 0, e to the I alpha. So it's easy to see that this matrix is unitary, right? So what's the definition of a unitary matrix? So a matrix is unitary if so T inverse is equal to T conjugate transpose. Okay, well, it's unfortunate that T appears twice here, but you can figure out what happens here. So this is a unitary matrix, and what it does is, so it does not move the first basis vector, and it implements a phase shift on the second basis vector. So it transforms 1 into e to the I alpha times 1. So it preserves the length and preserves orthogonality. So this is a unitary transformation. So these are all 1-qubit elementary gates that we will need. Clearly, we need more than just 1-qubit gates. Indeed, with 1-qubit gates, one cannot possibly create entanglement because 1-qubit gates operate on a single qubit at a time. So if we have a tensor product of states and apply 1-qubit transformation to a single qubit, then still we are going to get the tensor product state. So to create entanglement, we need at least to introduce 2-qubit gates. And one 2-qubit gate in particular that we will need will be this controlled phase shift. So let's call it S dot alpha, right? So it will be some analog, 2-qubit analog of the transformation S alpha that we considered. And so this controlled phase shift works in the following way. So when we apply S dot alpha to a tensor product of 2 qubits, X tensor Y, so then the result is, so it's going to be, so X tensor Y. If the value of X is equal to 0, so this means that if X is equal to 0, then we do nothing. And it's going to be X tensor S alpha applied to Y if the value of X is equal to 1, right? So basically, so if X is equal to 0, then we do nothing, and if X is equal to 1, then we apply this phase shift. But remember, this phase shift is applied only to the 1 bit. If we write this in the basis, then we get that 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. So this is because if the value of the first bit is equal to 0, then we do nothing. Then 1, 0 goes to 1, 0, right? So because S alpha acts identically on the first basis vector. And the only change happens when we apply this to 1, 1. So 1, 1 goes to e to the I alpha times 1, 1. Now, with this transformation, we can already create entanglement. So if we look at the state psi, which is the following, so 1/2 0, 0 plus 1/2 0, 1 plus 1/2 1, 0 plus 1/2 1, 1. So this state is unentangled. So because it can be factored as a tensor product of the following state. It's 1 over square root of 2, 0 plus 1 over square root of 2, 1. Tensor product with 1 over square root of 2, 0 plus 1 over square root of 2, 1. Right? So this factorization tells us that this is an unentangled state. But if we apply S dot pi with to this state psi, then well, this pi will give us e to the I pi. So this is equal to -1. So when we apply this controlled phase shift to the state, we're going to get 1/2 0, 0 plus 1/2 0, 1 plus 1/2 1, 0 and minus 1/2 1, 1. And now it is possible to verify that this state is already entangled. So this 2-qubit elementary quantum gate can create entanglement. And finally, so the 3-qubit elementary quantum gates are AND, so with the plus, and OR with the plus. So these are permutation gates that operate on 3-qubit space. In principle, so one can express AND plus and OR plus, so these elementary 3-qubit quantum gates, as compositions of 1 and 2-qubit elementary quantum gates. But still, it's convenient to have these nice gates at our disposal. And we leave the fact of possibility of such a decomposition as an exercise. Now we are ready to talk about quantum Fourier transform. So what's a quantum Fourier transform? So a quantum Fourier transform is a quantum implementation of the discrete Fourier transform. So let's recall what's a discrete Fourier transform. So the discrete Fourier transform is the following. So we take a sequence of length n, so f0, f1, f2, ... fn minus 1, right? So this is a vector in either real or complex n-dimensional space. So let's consider this to be a vector in a complex vector space. And so when we apply discrete Fourier transform, we get a sequence of Fourier coefficients, f0 hat, f1 hat, all the way up to fn minus 1 hat. Right? And so the formula for so fk hat is 1 over square root of n. Sum j goes from 0 to n minus 1. And here we have fj times e to the minus 2 pi I kj over n. So this is the formula for the Fourier coefficients. And so we start with a vector of length n, and we end up again with a complex vector of length n. And so one thing to point out is that this transformation is unitary, because so this discrete Fourier transform can be thought as a change of basis transformation. So we start with the standard basis in Cn, right? So this is considered as a temporal basis because here the progression in components is interpreted as progression of time. And so then we change the basis from temporal to the frequency basis. So we take as basis vectors now samples of exponential functions. And each exponential function corresponds to a particular frequency. And now, so these Fourier coefficients are the coefficients of representation of the same signal, but now as a linear combination of exponential functions. And so now this discrete Fourier transform is a change of basis transformation. And here we go from one orthonormal basis, so the standard basis of Cn, to another orthonormal basis. So we saw that these vectors that are samples of exponential functions, so these vectors form an orthonormal basis of Cn. And because we change from one orthonormal basis to another orthonormal basis, this transformation is unitary. But if we have a unitary transformation, we can interpret this as an operation on quantum space of bits, right? So in this case, we only need to set that n now is 2 to the little n, right? And so now we take this vector and we interpret it as a n qubit. We have the sum. X goes from 0 to 2 to the n minus 1. So we have fx times x. And so this is being transformed into another vector, which is the sum. Y goes from 0 to 2 to the power n minus 1. And here we have fy hat times y. Right? So this expression represents this vector of samples. And now we transform the vector of samples into the vector of Fourier coefficients. And so now this transformation is called Quantum Fourier Transform. And again, so this is going to be an element of a unitary group, u 2 to the power n. So this is our quantum task. So what we need to do is we need to realize this transformation. So we have a unitary transformation acting on the space of dimension 2 to the power n, so where it transforms a vector of samples into a vector of Fourier coefficients. And now we need to find an implementation of this algorithm. So in order to find this implementation, let us set up some notation. So what is x? So x here is an integer from 0 to 2 to the power n minus 1. But this integer is going to be written as an n-bit binary integer. So we're going to write it as xn minus 1, xn minus 2, dot, 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 x1, x0. So where each, so coefficient xi is either 0 or 1. Right, so this is an integer in binary form. And so basically, so we can write x in the following sum. So it's 2 to the power n minus 1 times x n minus 1 plus 2 to the n minus 2 times x n minus 2 plus 2x1 plus x0. So this is how we find the binary form of an integer. So we write it as a sum of powers of 2 with coefficients that are 0 or 1s. So now what we want to do is we want to find a fast algorithm for quantum Fourier transform. So we need to find a quantum algorithm that implements quantum Fourier transform. So this means that, so this is our input. Our input is n qubit, and our output is also n qubit, where in input we have samples of a signal, and in the output we have Fourier coefficients. And we want to find an algorithm. So this means that we want to implement this unitary transformation as a sequence of elementary operations that act on 1 or 2 quantum bits at a time. This quantum algorithm was actually known before Shor's work. And so this idea of using quantum Fourier transform was a key idea in the Shor's algorithm for integer factorization. Quantum Fourier transform is a linear transformation. So if we build an operator that does the right things on the basis vectors, so then this transformation will act in the proper way on all possible inputs. So now let us take a single basis vector x and see what happens to this basis vector, what should happen to this basis vector if we apply quantum Fourier transform. So this basis vector corresponds to, in these notations, to the following sequence. So we have f j here is equal to 0 if j is different from x, and it's equal to 1 if j is equal to x. So this means that this basis vector can be interpreted in the following way. So it's a linear combination where all values are equal to 0 except one value which is equal to 1. And so then what we see is, so this is being transformed into the sum y goes from 0 to 2 to the n minus 1. And here we have fy hat times y. Now, and what's the value of fy hat in this case? Well, we're going to use this formula, right? So, but keep in mind that this sum will contribute only one term when j is equal to x. And so then we get that fy hat is equal to 1 over square root of n. So this is 2 to the minus n over 2 times this exponential e to the minus 2 pi I. So here k is equal to y, and j is equal to x. So we have x times y over 2 to the power n. So we want to understand better this exponential factor. In order to do this, we write y also in binary form, just as we did here for x. So it's 2 to the n minus 1 y n minus 1 plus 2 to the n minus 2 y n minus 2 plus 2y1 plus y0. And so let's take e to the minus 2 pi I xy over 2 to the power n, and let's expand it according to this binary expansion. So I'm going to write it's in exp notations. So we have exp of minus 2 pi I times. So when we take 2 to the n minus 1, so here, so this 2 to the n minus 1 will cancel with 2 to the power n, and we're going to get, so x times y n minus 1 over 2 plus, so the next term will be x y n minus 2 over 4 plus, and so on. We'll end up with x y0 over 2 to the power n. But we also have an expansion for x here in this way. And what we see is for the first term, so all bits of x starting from the bit x1 are going to be irrelevant. Because if we take this term, for example, 2x1, then if we input this here, so 2x1 will, so the 2 will cancel, and we're going to get the integer x1 times yn minus 2. And exponential of an integer multiple of 2 pi I is equal to 1, right? So we have, so e to the 2 pi I k is equal to 1 if k is in z. So this means that we're only interested in fractional expressions that appear here. And so what we see here is that this exponential can be written as so minus 2 pi I. So from the first term, we will be only interested in x0 y n minus 1 over 2. In the second term, so here we have division by 4. So this means that only x0 and x1 will contribute. So we're going to get, so x0 y n minus 2 over 4 plus x1 y n minus 2 over 2. And so on. And for the last term, so all bits of x will contribute. So we're going to get, so x 0 y0 over 2 to the power n plus x1 y0 over 2 to the n minus 1 plus dot 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 plus x n minus 1 y0 over 2. And now the exponential of a sum may be written as a product of exponentials. So we get e to the minus 2 pi I x0 y n minus 1 over 2 times e to the minus 2 pi I. So we have so x0 over 4 plus x1 over 2 times y1 times dot 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 times e to the minus 2 pi I, and here we have x0 over 2 to the n plus x1 over 2 to the n minus 1 plus xn minus 1 over 2 times y0. Right? So now we have a product of exponentials. Now this should be n minus 2 here. Right? So now an important observation is that the first factor depends only on yn minus 1. And the second factor depends only on yn minus 2. And the last factor depends only on y0. This fact allows us to factor the image under q of t of the basis vector x. So here we can see that x under q of t must be transformed in the following product. So we take the sum where y n minus 1 goes from 0 to 1. And so here we have 1 over square root of 2, right? So we need these factors to build this factor 2 to the minus n over 2, right? And here we have e, so we put this factor, minus 2 pi I x0 y n minus 1 times y n minus 1. Right, so we take this sum, tensor with the second factor will be the sum y n minus 2 goes from 0 to 1, 1 over square root of 2 e to the 2 pi minus 2 pi I. So here we have x0 over 4 plus x1 over 2 times y n minus 2 tensor and so on. And the last tensor factor will be the sum. So y0 goes from 0 to 1. We have 1 over square root of 2. And here we have e to the minus 2 pi I. And so here we have x0 over 2 to the n plus x1 over 2 to the n minus 1 plus x n minus 1 over 2 times y0. And so this is times y0 here. And likewise here, we should write times y n minus 2. Right? And so what we see here is under quantum Fourier transform, each basis vector is transformed into something unentangled. Of course, this does not mean that q of t does not create entanglement, right? So because it could take some unentangled state, which is different from a basis vector, and it will transform it into some entangled state. So it's just when applied to basis vectors, the result is unentangled. And we're going to take advantage of this fact. So also note that these distributed factors 1 over square root of 2 will combine and will give us the overall factor 2 to the minus n over 2. Right, so because there are n factors of this type here. And so we do this so that each factor has norm 1. In order to understand this state better, let us write each sum as a sum of two terms. So what we will get here is the following. So if yn minus 1 is equal to 0, so what's the value of this exponential? Well, if yn minus 1 is equal to 0, then this exponential becomes e to the 0 of 1. So the first term in this sum will thus be 1 over square root of 2 times 0 plus, now I should point out that here we were missing a denominator, so this should be divided by 2. So when yn minus 1 is equal to 1, then we're going to get the following coefficient: 1 over square root of 2 e to the minus 2 pi I x0 over 2. Now, yn minus 1 is equal to 1 times 1. Right? So this is our first tensor factor. The second tensor factor will be, so here again, if yn minus 1 is equal to 0, then this exponential turns into 1. So we have 1 over square root of 2 times 0 plus 1 over square root of 2, and then the coefficient is exponential, e to the minus 2 pi I. And if yn minus 2 is equal to 1, then it will just disappear. So we get x0 over 4 plus x1 over 2 and times 1. And tensor product. And so we take all these tensor product factors. And the last tensor product factor will be, so this one, so it will be 1 over square root of 2 times 0 plus 1 over square root of 2 times e to the minus 2 pi I. So, and we have x0 over 2 to the n plus x1 over 2 to the n minus 1 plus xn minus 1 over 2 times 1. So we have this tensor product. From these formulas, we see that the computation of the highest bit yn minus 1 of the output depends on the lowest bit of the input. And so for the second highest bit of output, we need to use 2 lowest bits of the input, and so on. So it will be advantageous to organize our quantum Fourier transform in such a way that here we're going to write input and output bits in different order. So this means that for input bit, we're going to write it as x0, x1, all the way up to xn minus 1, right? And so this will be transformed into qft, into the sum over y, f hat y, times, here we're going to write yn minus 1, yn minus 2, all the way up to y1 and y0. So this means that it will be easier to transform x0 into yn minus 1. So the changing of order of bits of x could be implemented by a simple swap of bits. So we could apply 2-bit transformations acting on the first and the last bit, then second and second last, and so on. So this swapping can be easily done. Now, let us see how we can transform the qubit x0 into qubit corresponding to yn minus 1. So essentially, this corresponds to this factor here. So if we start with our qubit x0, right, so then so it transforms in the following way. So if x0 is equal to 0, then it will be transformed into 1 over square root of 2, 0, plus 1 over square root of 2, 1. And if x0 is equal to 1, then the image is 1 over square root of 2, 0, minus 1 over square root of 2, 1. Right, so this is because e to the minus pi I is equal to negative 1. And so what we see is that this transformation is nothing else but the Adamar's transformation H. So here, basically, all we do to the leftmost qubit is we simply are applying the Adamar transformation. So if we look at the remaining qubits, then we see that we also have Adamar's transformation built in there. So for example, if we just forget about this term with x0 over 4, right? So if we just keep only this term, then this will be an Adamar transformation applied to the bit x1 and creating the qubit yn minus 2. So this means that we need to apply Adamar and then do something else that will create us this term here. And likewise here. So if we just take only this term, then and drop the previous terms in this sum, this will be an Adamar transformation acting on xn minus 1 qubit and transforming it into y0 qubit. Let us look at the first two factors and see how we can implement quantum Fourier transform just on the first two factors. So we start with the input, which is a qubit x0, x1. And so let us apply Adamar on the tensor factor, right? So this means that we take identity transformation on the first tensor factor and Adamar on the second. So this will give us x0 bit tensor. So the value of Adamar will be 1 over square root of 2, 0. And as we said, that the second term of the Adamar can be written as 1 over square root of 2 e to the minus 2 pi I times x1 over 2 times 1. Right? So if x1 bit has value 0, so this will transform it with a plus. And if x1 bit has value 1, so this will transform it with a minus. So this is precisely will be the Adamar transform on the second quantum bit. So after this, so now we need to create this contribution of x0 over 4. So this means that if x0 is equal to 0, then we do nothing. And if x0 is equal to 1, then we do a phase shift on the 1 vector with angle minus pi I over 2. This corresponds to controlled phase shift by angle minus pi I over 4, where this shift is applied to the second bit, and it's controlled by the value of the first bit, right? So this will transform this tensor factor into 1 over square root of 2 times 0, right? So this phase shift does nothing on the first basis vector. And on the second basis vector, we apply the shift. But the shift is controlled by x0. So what we get is 1 over square root of 2 e to the minus 2 pi I times x0 over 4 plus x1 over 2 times 1. And for the last step, so we apply the Adamar transform on the left qubit. So if we now apply the Adamar transform on the left qubit, then what we're going to get is 1 over square root of 2 times 0 plus 1 over square root of 2 times e to the minus 2 pi I times x0 over 2 tensor with this qubit here. So 1 over square root of 2, 0 plus 1 over square root of 2 e to the minus 2 pi I x0 over 4 plus x1 over 2 times 1. In this way, we obtain the quantum Fourier transform for 2-qubit expressions. And now it's not too difficult to see the general pattern. So basically, we're going to work backwards. So first, we're going to apply the Adamar transform on the last qubit, on the rightmost, And so this will implement this contribution here. And so then after this, we apply controlled shifts to the last bit that are controlled by x0, x1, and so on, each with appropriate angle. And so then after we create the value of the last bit, you see, the previous bits do not involve x n minus 1. So the leading term of the input only affects the last y0 bit of the output. And so then we just move to the previous bit, we apply the Adamar there, and then we apply controlled phase shifts by the previous bits, and so on. And we finish by applying Adamar to the leftmost bit. So here is the quantum circuit for quantum Fourier transform. So as we can see here, so in the last bit xn minus 1, we first apply Adamar transform, and then we apply controlled phase shifts by all previous bits here. Right. So then in the second last bit, so after we applied the controlled phase shift from second last bit to the last bit, then here we apply Adamar, and then we have controlled shifts from the previous bits. And finally, for x1, so after we applied all controlled rotations to the higher bits, so we apply Adamar, and we apply controlled rotation by the bit x0. And in the bit x0, we just apply Adamar, and this gives us the leading bit yn minus 1. And so in this way, we see that we get the diagram for quantum Fourier transform. And each quantum elementary gate in this diagram is a quantum gate either on a single bit, so the Adamar, or on a pair of bits. So these are elementary quantum gates. So now let's calculate the complexity of the quantum Fourier transform. So what we see is that for the last bit, we apply n gates. Then for the second last bit, we apply n minus 1 gates. And all the way that for x0, we apply just a single gate. So what we see is that the complexity is n times n minus 1 over 2. But keep in mind that this little n is log base 2 of the capital N, right? So because capital N is 2 to the power n. So what we see is that the complexity of quantum Fourier transform is quadratic in the number of bits, whereas for fast Fourier transform, so the complexity was n times 2 to the power n, right? So it was linear in the number of terms, right? But it's exponential in the number of bits. And here we get quadratic in the number of bits, so this is incredibly better than this one. So this explains why Shor's algorithm is so efficient. It has quadratic complexity in the number of bits, whereas all other known classical algorithms have exponential complexity in the number of bits. So what we have here is a quantum algorithm implementing quantum Fourier transform with quadratic complexity.